So yesterday we were looking to arrive at a derivation of the result that we had claimed to be true. We had said there was this function f of x, right, which is continuously differentiable, right? And we said that if you have a point x star belonging to this domain D, yeah, where does D come from? D is sitting inside the n-dimensional Euclidean space. What had we said about D? What was true of D? Any property that we had attributed to D? Open set. Why did we need the open set? Just to refresh or jog your memory. We can draw an open ball around every point in an open set. Fantastic. So we'll always be able to find an epsilon such that an epsilon ball can be drawn around every single point. So every point in D is an interior point. At least that is clarified, right? So we said that this, for this point in the n-dimensional Euclidean space contained inside this open set D therein, for this to be a minima, we need the grad of f evaluated at x is equal to x star to be 0. This is what we had claimed, that this is a necessary condition. Of course, it begs the question, why should it be so? In order to do that, if you recall, we did the following. We defined this function in a single variable g of alpha like so. Yeah, for some v in Rn such that v was a unit vector, right? This was the setup. Yeah, this is all a repetition of what we had seen the other day, just to jog your memory so that we set the record straight, right? Now, what could we say about the minimization of this function in terms of alpha? To claim that f of x star is indeed the minimum value that this function attains within this open ball D is the same as claiming that g of 0, yeah, is the minimum that is attained in terms of g. The difference being that now when we talk about it in terms of g, we are talking about it in terms of a scalar. It's been parameterized. Of course, it comes at a cost. You see, the domain of f is a subset of the Euclidean space. So you could approach that point x star from all sorts of possible different directions. But now by varying this parameter alpha, you're only going to travel along one such direction which is specified by v. Okay, so there is that issue. I want you to keep that in mind. We will address it before we close this. Okay, but let's for the moment just focus on this one direction along which we are traversing for the time being. In fact, so much so, you could actually associate this g with a subscript v to denote that you're only talking about traversing along the direction of the vector specified by v. Okay, it's a matter of taste really. I'm not going to do that. Towards the end, we'll present an argument where the specific direction of v will not matter. Okay, all right. Now that we are in the domain of a scalar, or function of a scalar, what can we say about g? Can we not write the following is equal to Yeah. What is this a consequence of? Can anyone tell me? What have I written here exactly? Should be familiar, no? Yeah. So what's being said with all of this here? It's being said that these are higher order terms essentially. They traverse towards 0 at a rate that's faster than alpha, right? That's the reason why as alpha tends to 0, this term tends to vanish quicker than alpha, faster than the linear rate. Yeah? Clear, right? So this is pretty standard stuff. We know this. Any doubts on this so far? Nothing other than Taylor series is being addressed here. Okay, so this is not really something fancy, it's standard stuff so far, right? So what can we say about this now? You see, we have claimed that g of 0 should be the minimum value attained by this, which means that if we are taking this g of alpha minus g of 0 here, what should it be? It's a scalar, of course. What can you say about this number? It's going to be a positive number, right? Because you're going to increase. If g of 0 is the minimum value that you can possibly attain, then g of alpha must be greater than that g of 0. This must be positive. At this point, we're going to make a tertiary sort of a claim. Okay, bear this quantity in mind. We're going to claim that, this is our main claim by the way, this is the main claim. On our way towards establishing this claim, we are now going to claim the following. We're going to claim that this must be equal to 0. So maybe I'll write this with the regular handwriting. It's a smallish claim that will lead us to this bigger claim. This is what we're going to now establish first. Why must this be true? Once again, turn your attention to this object here. And let us write it from there as alpha g prime 0 plus these higher order terms here. Suppose in contravention with this claim, we say that g prime 0 is not equal to 0. So we are contradicting that claim, and let's see where that leads us to. Yeah, look at this here. If I now impose a signum function on either side, they would either both be plus 1 or both be minus 1. Yeah, because these are equals. So the signum of this is the same as the signum of this. Now, since gets smaller as alpha tends to 0, what might we say? Choose alpha such that the modulus of this fellow predominates the modulus of this fellow. You can always do that, isn't it? This fellow gets smaller and smaller, right? So beyond a certain point, this is a fixed number, apparently non-zero according to our contradiction. We are trying to prove that this is 0, but in the process we are contradicting this and saying that suppose this is non-zero. It's some number, so if the modulus, the absolute value of this is some positive number. Yeah, so if you keep making alpha smaller and smaller, beyond a certain point, this term will get smaller than this because it has to approach 0 continuously in the limiting sense. So after a point, it's below this bound. It never overshoots this. Yeah, so that's the kind of alpha, the range of alpha values that we are looking at. Yeah, what happens in this situation? Let's go back to the sign of g alpha minus g 0, which is equal to the sign of, what was the term? Alpha G prime 0 plus this. What can we say about this for this situation, for such a choice of alpha? Once we have chosen such an alpha, what can you say about this? Just think very carefully. It's staring us, it's right there before us. I can't say positive or negative yet, but I can certainly say something about this. Okay, just a few small little tricks here. I mean, look. Sorry. Is this any different from Isn't this true? That's just a small little hint. So what can we say about this? What is the signum of this term going to be equal to under this given situation? I mean, you have, say, a number such as 5 and another number, a number whose magnitude is, say, 5, and another number whose magnitude is less than 5. Whether you subtract the second number from the first number or add to it, does it change the sign of the overall resultant? I mean, if this is minus 5, whether you add 3 to it or subtract 3 to it, it still remains negative. If it's plus 5, same thing, whether you add 3 to it or subtract 3 from it, it still remains positive. So the signum of this is actually the same as the signum of just the first term, right? We still don't know whether it is positive or negative, but it's nonetheless the same as this. But here is the catch. Have I restricted my alpha to be, I mean, in terms of its sign? Alpha could be any real number. If you have a direction V, for positive alpha, you're probably heading in one direction. For negative alpha, you're heading in the exact opposite direction. The direction specified by V extends in both directions. It's not a ray, it's a vector that extends along both the positive and the negative directions, right? So now, if alpha and G prime 0 have opposite signs, what happens? Then what happens? What is the consequence? This is going to be a why positive? Positive can only happen if they have same signs, no? Plus and plus, minus and minus. If they have opposite signs, one of them definitely has plus, the other definitely has minus. So their product is negative number. If the product is a negative number, then this object is minus 1. So is this object. Yeah. Then G of alpha minus G of 0. Now I'm getting rid of the signum and we have this, which means what exactly? That by proceeding along that suitable direction, either along plus direction of V or along the opposite direction of V, you can do better. And you can always push along such directions because you are living inside an open set. Even if infinitesimally so, even if by a small quantity or by a small distance, you can always proceed along both the plus V direction and the minus V direction. So there always exists a direction which allows you to do better than what you are doing at the point given by alpha is equal to 0, that is x star. That shouldn't be the case. You cannot find any neighborhood within which x star is the best. There's always a better direction. There's always a better point, so to say, which is better at minimizing this. That's the contradiction. Where did this contradiction arise from? From the first premise where we said that G prime 0 is not equal to 0. Indeed, if it were equal to 0, all these steps would fall apart. Exactly, right? So therefore, all this arose because, so this is a contradiction to the claim that this was the best, x star was the best point, right? Therefore, we must have G prime 0 is equal to 0. At least that is established. Okay? But we are still not seeing the light at the end of the tunnel, which is essentially this. We are still talking in terms of G, not in terms of the original F. Yeah? Let's see how we can get there. We'll have to relate the G with F, and of course we have defined it. We've said that G of alpha is equal to, by definition, F of x star plus alpha V. Right? Now, what we know is that G prime 0 is equal to 0. This implies that if you take the derivative with respect to alpha of this and therefore of this, that must vanish. Yeah. So we're going to do that. F of, I'm going to just write this in a somewhat clumsy manner, but it will provide more clarity hopefully. Right? You're agreed that this is exactly what it's equivalent to, what it's tantamount to. Yeah. So what do we do now? Of course, we apply a good old differentiation using chain rule. Remember, this object is taking the place of x1. This object is taking the place of x2, and similarly, this object is taking the place of xn. So by chain rule, this is a function in n arguments. So by chain rule, each of them is parameterized in terms of alpha and alpha alone, because x1 star, v1, x2 star, v2, these are all constants according to the choice of the point x star and the choice of the direction v. So they don't vary. The only variable here is alpha. Right? So what does this tell us? When I take it with respect to the first variable, what is it? I have to take it with respect to the first argument here. Yes? But then I have to take the derivative of the first argument with respect to alpha. What does that give me? Yeah? This is evaluated at x star plus, now I'm going back to the shorthand notation, alpha v. Yeah, okay, of course, I'll just say that this is at alpha is equal to 0, just so that you remember. This is what exactly? What comes in here? When the first argument is differentiated with respect to alpha, you just get v1, v1 plus just products of scalars, right? Plus dot 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 plus all of this taken at alpha equal to 0 must be equal to 0. But then what is it after all? It's a dot product, right? Dot product between the gradient of f evaluated at x star and the vector v. So this essentially means the gradient of f evaluated at x is equal to x star, its dot product with v must be 0. Yeah. We are still not claiming that grad of f is exactly equal to 0, but we are very close to claiming that. Can you tell me what is the argument that will help us cross the final frontier and say that indeed just this object taken in and of itself will vanish? Sorry? V is arbitrary. Fantastic. That's exactly what the point is. Because V is arbitrary, what could you possibly have chosen V to be? One possible choice of V could have been what? The direction along the grad of f at x star? No. There's so many ways of arguing about this. This is a vector. This grad of f evaluated at x star is a vector whose inner product with any vector in the Euclidean space vanishes. What is the only vector whose inner product is with every vector vanishes? It means it's orthogonal to every vector. What is the only vector which is orthogonal to every vector? It's just a zero vector. That's one way of saying this is zero. Another obvious way of seeing that this is zero is, since this choice of v was arbitrary, choose this v to be along the same direction as the grad of f evaluated at x star. Therefore, a inner product of a vector with itself, of course subject to a scaling because it's a unit vector, doesn't matter. If the inner product of a vector with itself is 0, it means the norm of the vector must be 0 and therefore the vector must itself be 0. Yeah. So therefore, this immediately implies that grad of f at x star must be 0, and we have established the first order necessary condition for minimality. In fact, it's also the first order necessary condition for maximality. Just replace f with minus f, the whole argument carries on exactly in the same manner. There's no difference. Yes, so this is actually the first order necessary condition for optimality. Necessary, not yet sufficient, because there are certain other things that we need to be mindful of. This is the first order. Of course, the assumption was that f was continuously differentiable. Okay. If you want to find the global minima for a function, what would your strategy now be? Given a domain of the function, find out all points where this fellow vanishes. Sorry. Oops. Find out all points where the grad of this function vanishes. Yes, list out all those points and find out the point where it attains the smallest value computationally. Right? That's the most logical thing. So this at least allows you to shortlist from an infinite number of points in the Euclidean space or in the domain of a function. At least you shortlist a few points, candidate points, which satisfy this condition. These are the critical points. Yes. So you make a list of these critical points, find out the value of the function at these critical points, find out the one critical point where the least value is attained, and you have the global minima. Yeah, if there are multiple points attaining the same global minima, then there's no unique global minima. Okay. There are some special nice properties which sometimes allow you to get to a unique global minima. We'll probably briefly chat about it a while back. But now, since we are in the realm of at least seemingly wishful thinking, let us now extend this a little further and say that suppose f is twice continuously differentiable, and therefore we shall now try and see if we can similarly arrive at second order necessary conditions for minima, or by the same token maybe for optimality. Okay, that's what we shall see next.